So let me welcome you all to this session of the this conference. And in this session, Monika will be for the next 1 hour. Monika will be talking about synergy of flavor with the energy and cosmic frontiers. So and as probably you have heard that you can ask questions if it's a very urgent one. Otherwise, you can note the slide numbers and you can ask at the end. And she has two parts, and so after completing one part she will be you will be allowed to ask questions, so you can ask questions at the time. Otherwise, at the end you can ask questions. So Monika, please, you can
Yeah, so thank you very much for the kind invitation to your meeting. And let me start by briefly introducing myself. My name is Monika Blanke. I work at Karlsruhe Institute of Technology, and I'm a particle theorist interested mainly in flavor physics beyond the standard model and its connections with the high energy and cosmic frontier. And the synergy between these three fields is also the focus of this talk. Now let me start by motivation. Why is it interesting to study flavor beyond the standard model? Well, first of all, we know that already in the standard model, flavor and also CP are not good symmetries because they are already violated in the standard model by the Yukawa couplings and the resulting CKM matrix. In addition to that, any concrete BSM model will generically also introduce new sources of flavor and CP violation beyond the ones that we have already in the standard model. And last but not least, we also have a good phenomenological motivation to study flavor beyond the standard model, and this is the B meson anomalies. We have seen various anomalies related to B meson decays, which currently provide one of the most promising experimental hints for the breakdown of the standard model at or around the TeV scale. Now, flavor physics is only one part of the particle physics world, but there are also the other parts, namely the high energy frontier, often referred to as collider physics, or also recently LHC physics, because that's the main accelerator at this moment. And thirdly, also the cosmic frontier related to questions concerning dark matter, dark energy, baryogenesis, and so on. And the question is then, how are these different subfields of dark matter connected? And can we maybe profit from some synergies between these various subfields? In order to address these questions, I would like to discuss two examples for possible synergies between these different fields. First of all, I will focus on the B anomalies and their complementary probes at the LHC. And in the second part of my talk, I then want to discuss the concept of flavored dark matter and its LHC signatures. So the second part of the talk really focuses on all three fields, flavor, cosmology, and collider, while the first part is a little bit external to the cosmology question. Now let me start with part one, B anomalies and complementary probes at the LHC. And here, to be specific, I want to concentrate on the anomaly in the ratios RD and RD star. So these ratios are tests of lepton flavor universality in semi-leptonic B decays, in the decays of a B meson decaying into a D or D star meson and a lepton-neutrino pair. And the ratio then takes the rate into tau final states versus light lepton final states. And as it turns out, there has been a tension in these ratios between the standard model prediction and the data already for 10 years now. Now, why are we so excited about this? Well, on the one hand, these ratios are theoretically rather clean because the hadronic uncertainties and also the uncertainties related to the CKM element VCB driving these decays largely cancel in the ratio. And second is the fact that there is not only a measurement by a single experiment, but in fact we have data from three different experiments, Barbar, Belle, and LHCb, that all give us a consistent picture of these ratios RD and RD star, and point overall to a 3.4 sigma anomaly with respect to the standard model. Now, thinking about this anomaly in terms of new physics, it's useful to first start with a model-independent description of the new physics contributions. And to do that, it's useful to construct the so-called effective Hamiltonian, where you write down all possible 4 fermion interactions between a B quark, a C quark, a tau, and a neutrino, And the various spin structures of these interactions then give you these several 4 fermion operators. And the model-independent way of parametrizing new physics in this effective Hamiltonian is then done in this way that you simply introduce these Wilson coefficients in front of the various new physics operators that then parameterize the type of new physics that you're introducing. Now, how do these Wilson coefficients relate to concrete new physics models? Well, in the case of this anomaly, it's actually quite easy, because all successful new physics scenarios in this case actually rely on tree-level contributions of new particles, simply because the new physics effect you need is relatively large. So you cannot try to construct loop models for this anomaly. And the various new physics fit scenario then basically boil down as is written on the slide. So first of all, you can think about introducing a W prime boson, which would be essentially a partner of the standard model W boson, but with heavier mass and with somewhat different couplings than what you have for the standard model W. Unfortunately, it turns out that such a W prime solving the anomaly is already disfavored by electroweak precision constraints, and hence I will not discuss it any further. What remains as possible solutions are on the one side, the possibility of having a charged Higgs boson being exchanged in the semi-leptonic transition. And on the other hand, you can construct various leptoquark scenarios. And for the leptoquarks, there is one which is particularly interesting in my view, and that is the case of a spin-1 vector leptoquark, which can solve this anomaly, as you will see later on. Now, what do we learn from the Flavour data on these different new physics scenario? Well, in that case, it's useful to go back to the effective Hamiltonian description and fit these Wilson coefficients to the data on RD, RD star, and related Flavour observables. And when doing these fits, it turns out that actually various of these models that I've just introduced on the previous slides can give you good fits to the data. In particular, both the charged Higgs solution and also the vector leptoquark scenario work well with the Flavour data. And I would also like to point out that the charged Higgs model, which has been heavily discussed in the literature, predicts a very large branching ratio of a B sub C meson into a leptonic tau plus neutrino final state. This has been discussed heavily in the literature because there were some claims that this is actually excluded by the total B sub C lifetime, but a more recent assessment of the theoretical prediction of that lifetime has shown that this prediction is not actually excluded, and the charged Higgs is still a viable possibility from this point of view. And last but not least, the purple exclusion contours in these plots show you that these fit results are also in agreement with current constraints from Monotower searches at the LHC. And I now want to explain a little bit more what these LHC Monotower searches actually are. So the idea is that if you have such a decay of a P quark into a C quark, a tau and a neutrino, you can relate it via crossing symmetry to processes in which you put the quarks in the initial state of 2 colliding protons, and yet then you produce final states, including a single tau lepton and a neutrino, which then corresponds to missing energy experimentally. So this means that these monotau plus missing energy signatures actually serve as a good probe for new physics models for the RD and RD star anomaly. And various phenomenological analysis of these monotau searches have shown that already with the current data, LHC B has become competitive in testing the anomaly. On the one hand, these studies show that the vector leptoquark is one of the models which is actually the least challenged by the current data. So this is still currently completely fine with these monotau constraints. While on the other hand, the charged Higgs case is more constrained. And for that case, it's actually a little bit more complicated than what I'm just showing here on the slide, because the charged Higgs would be produced resonantly from fusioning a B quark and a C quark, and then the charged Higgs decays into tau nu. So you have to look for a resonance in the decay. And from these resonance searches in tau nu final states, it actually turns out that the charged Higgs solution is indeed ruled out, provided the charged Higgs mass is larger than 400 GeV. So then the next question is, well, if it's excluded for more than 400 GeV, what about less than 400 GeV? So a light charged Higgs for the anomaly. And this case is actually not excluded by the monotau data. And the reason is that you get a huge standard model background from the tail of the W boson decaying into tau plus neutrino. So in this case, we need to be a little bit smarter than just looking for tau plus neutrino. And the idea here is that in addition to tau and neutrino in the final state, we can also demand the presence of an additional B-tech jet. So this works as follows. Basically, you take the B quark from the charged Higgs coupling and pull it from the initial state to the final state. And then your total signature would be a B quark or a B-tech jet, a tau lepton, and missing energy. And the question is then whether demanding this additional B-tech jet would actually be sufficient to exclude the charged Higgs solution also for light masses for the RD and RD star anomaly. And we addressed this question and tried to design a search for such a B tau nu signature. And here is our result. Well, first of all, we have found that the charged Higgs close to the top threshold is actually the most difficult case to exclude, because this is the lightest possible case where you're just slightly above the top mass. You cannot be below the top because then you would alter top decays. And the lighter your charged Higgs is, the more similar your decay distribution will be to the standard model W to tau nu distribution. So hence, this case is relatively difficult to work on. However, even in this case, we have relevant constraints already from other observables. In particular, in red, you see the constraints from tau searches in supersymmetry. So these are the lepton partner of the tau lepton of the standard model. And also in blue, there are constraints from searches for digit resonances at the LHC. And our new results from the B tau nu signature are shown by the black dashed line in the plot here. So for 139 inverse femtobarn, which is the total Run-2 data set, you see that our search would give you a quite strong exclusion contour already. And there's only a pretty small parameter space of the model left where you can resolve the anomaly and which would not be probed with the current data. And if you then also, at the same time, also use the full available data set for the digit exclusion, you would move from this band here, which has been based on 36 inverse femtobarn, again to the dashed line. So this would be the corner of parameter space next to this red sun here that could not be probed by the current data, but still resolve the RD and RD star anomaly. Clearly then, if you move on to future runs of the LHC, which are now starting already, but with particularly the high Lumi phase of the LHC will still take a lot of time, we can then obtain a final verdict from the LHC on whether the charged Higgs solution to the RD and RD star anomaly is viable or not. Now assume for a moment that charged Higgs is now taken care of and either ruled out, well, probably ruled out by these searches, then the next and final target for this anomaly would be Leptokwa models. And Leptokwa models might appear to you as being something rather exotic. You don't have leptoquarks, meaning particles coupling quarks to leptons in the standard model. And you might not have them in your favorite new physics model, maybe supersymmetry, Z prime models, or so on. However, I would like to point out that these leptoquarks are actually not as exotic as you might think. And in fact, they are present in any theory unifying quarks and leptons. They also turn out to be the favored solution for the B anomalies. And in particular, the favored solution would be this vector leptoquark that I've already mentioned before, which is often denoted U1 in the literature. And in the coming slides, I will also denote it as delta as simplicity. Now, why is this solution so particularly popular? Well, the first reason is that this leptoquark is in fact the only single particle scenario that can solve both the RD star and also the B2S mu anomalies. By doing this, it is compatible with other flavor constraints, and it does not induce proton decay. Last but certainly not least, it's also attractive from a more theoretical or model building perspective, because this new spin 1 vector leptoquark is actually naturally contained as a degree of freedom in the Partisalam gauge group, in which the 3 colors of QCD and lepton number are unified into a 4-color theory, so that you have SU4C instead of the standard model SU3C. Now, when building such models, I would like to stress that the main obstacle that you have to overcome is that for such a leptoquark, you need to implement a non-trivial flavor structure in the couplings of the leptoquark to the standard model quarks and leptons in order to address the anomalies. Now, instead of pursuing the model building path further, I want to focus now on simply the minimal coupling structure for this vector leptoquark model that can solve the RD and RD star anomaly, so we stay within the simplified model framework. And the minimal coupling scenario that you need is the so-called tau isolation pattern, in which you couple only to the 3rd generation leptons, so only to tau and the tau neutrino. And also, you don't need a coupling to the 1st generation quarks, since the anomaly is in B2C transition. So you are left with this coupling structure here with lots of 0 in the 3x3 matrix, and only 2 couplings that are left. B tau is the one which is pretty obvious why you need it. And then the S tau coupling is related by SU2 symmetry to the coupling of a charm quark to the neutrino. And it turns out, while this coupling structure is actually rather minimal and the most minimal thing that you can think of writing down, it is actually not as ad hoc as you might think, but it is in fact compatible with the assumption of having discrete flavor symmetries in your model. Now, taking this minimal coupling pattern and plugging it into the software performing global fits to the available flavor and electroweak precision data, you can find the result that is shown here on the right-hand side of the slide. The constraint from RD star is given by this black band, and the global fit is given by the yellow and blue contours representing 1 and 2 sigma. And you see that the anomaly is actually quite well resolved and being consistent with the global flavor fit. What I've also introduced in this plot are these red dots here, and those are benchmark points that we have defined. They will be interesting for our subsequent collider analysis. And what is interesting to note about these benchmark points is that for all of them, actually, the predictions for RD and RD star are basically equal to each other. So just using the flavor data on these semi-leptonic transitions will not help you to distinguish which of these parameter points is actually realized in nature. And this is where LHC can come in at your rescue. So the problem, again, with measuring only these flavor observables, RD and RD star, is that they constrain a particular combination of parameter. Namely, they constrain the product of these 2 coupling parameters divided by the ratio of the leptoquark mass squared. However, we also want to determine the parameters of the model independently. And this is what LHC can do for you. Because first of all, you can determine the leptoquark mass by pair producing the leptoquark, and from the pair production cross-section, you can get a handle on the mass of the leptoquark. And in addition, also from the decay products of the leptoquark, you can measure the invariant mass and thereby determine the mass of the leptoquark. And then the final question is, how large are these 2 couplings individually? And in order to address that question, you can measure the branching ratio of the leptoquarks into different final states. And you see that these leptoquark branching ratios are actually proportional to the ratio of these 2 coupling constants. So then by determining both the ratio and the product, you have determined all of the parameters independently. So from this, you can already see that there is quite a strong synergy between flavor and collider data in order to fully determine the leptoquark parameters. You can neither go for only LHC data, nor you can go only for low energy flavor data, but you need both of them together in order to fully constrain the model. Now, I was talking about pair production of the leptoquarks previously in order to determine the mass, and actually pair production is also the main channel for producing these leptoquarks at the LHC, as long as they are not too heavy. And in this case, the picture of different branching ratios gets a little bit more interesting again, since instead of just one leptoquark decaying to different possible final states, you now have two. And that gives you a whole table of different possible final states that you can look at. And I would like to point out in particular the one that I highlighted here in red, which is the final state of one B quark, one tau lepton, one top quark, and one neutrino in the final state. Certainly this is interesting from the experimental point of view, because all of these particles give you quite distinct signatures at the LHC. And second, as you can see from the color chart in this table and also from the numbers, is that for these different benchmarks points that we selected throughout the parameter range of our model, the rate for this final state actually varies quite strongly. So measuring this final state would certainly be a good target in order to determine the leptoquark coupling parameters. Unfortunately, however, we haven't discovered any leptoquarks yet. Nonetheless, we have at least an experimental analysis targeting this final state, the B tau top new final state, which unfortunately, as I said, didn't see any signal of new physics, but instead, at least we get some constraints on the model. And we did perform a reinterpretation of this existing experimental analysis, leading you to these exclusion contours that you can see on the right-hand side of the slide. So don't worry too much about the two different colors. These are essentially two different scenarios for a further parameter of the model that I don't really have time to introduce right now. But what you see is that these exclusion contours given by the solid lines in the plot depend quite strongly on the ratio of these two coupling parameters, as predicted, since this ratio drives the branching ratios of the leptoquarks. Now, this is, however, not the only LHC constraint on the model we have. And in fact, we also performed a checkmate analysis to see what other constraints are relevant. And we found that strong constraints also stem from the final states with having a certain, several numbers of jets in association with missing energy in the final state. Now, these final states turn out to be much less sensitive to the leptoquark coupling pattern than this rather distinct final state, since you have jets both from the first two generation quarks and also from the third generation. And in that sense, these dashed lines here, which represent these bounds, are complementary to this B tau top neo search because they cover some additional parameter space that this search is not sensitive to. Now let me come to the summary of the first part of my talk. And I've shown you that the B anomalies currently provide one of the strongest hints for BSM physics, and dedicated LHC searches yield complementary information on the underlying new particles and their coupling structure. I've shown you this by the example of looking at the RD star anomaly, where we have seen that the charged Higgs explanation is actually on the verge of being excluded by the LHC data with a B, a tau, and a neutrino in the final state, while on the other hand, the leptoquark pair production process with different final states can actually shed light on the coupling structure of such models. So with this, I would like to conclude the first part of my talk, and I would briefly like to pause for questions from the audience.
Yeah, then anyone have any questions? Please go ahead.
I have raised my hand. Can I ask a question?
Okay.
Yes.
Yes, sure.
Okay. So, Monika, hi, this is Rohini. And
hi.
nice to hear you. So, I had a few questions. So on your first slide itself, you said that the B physics anomalies indicate a TeV scale new physics.
Yes.
Now, that I imagine you're saying because you are really focusing on the RD star, right? I mean, other anomalies don't necessarily
in the slide I wrote at the TeV scale. When I was talking, I said at or around the TeV scale, and I fully agree that for RD star and RD, it's really at the TeV scale. For the BS mu anomalies, you can actually go to more like 30 or 40 TeV in most unlucky case. So that's a little bit beyond LHC, I agree.
So we agree on this. Okay, good, thanks. Now, absolutely. Can you go to your slide 9, 10, you know, where you were discussing the charged fixes?
Here?
Yeah, because it's 9, slide 9. After that, yeah, here. Okay. So first, this was sort of a minor question that this dark gray and light gray shades, they really just correspond to the regions for the different values of the predicted values of the branching ratio for BC to tau nu. Is that correct?
Yeah, exactly. So there's a lighter gray region which corresponds to the branching ratio BC to tau nu being above 30%. Then this 30% was a limit that was put forward in the literature some years ago based on the total B sub C lifetime. And then in our study 3 years ago, we pointed out that there is actually more room for new physics in there because the prediction is not as bulletproof as it might seem. So you can actually go up with this branching ratio to about 60%, which would be the dark gray contour here.
Okay.
And also in a more in-depth calculation of the total B sub C lifetime done last year, I think, by Eberscher and Greenstein, it was confirmed that you can actually have such large value for this branching ratio while being compatible with the total B sub C lifetime.
Okay. No, thanks.
So the dark gray contour is really what you should take as the current status.
As
now.
the sort of the ultimate.
Yeah.
Okay. Now, Soumitra, can I ask one more question?
Yeah, go ahead, no problem.
Okay. So my last question is a more general question, Monika, that why is the vector leptoquark so much more preferred over scalar leptoquark? Because in some sense, in supersymmetry, we have very happily scalar leptoquarks without even going to unification. So I'm just curious, on general grounds, can one understand this?
I think the main reason is not so much from the theory perspective, because in many models you have scalar leptoquarks as well, as you mentioned. You have them in supersymmetry without R parity. You also have them for instance, in a general Party-Salam model or some other unifying model. You would in general also expect scalar leptoquarks. It's totally true. I think the main reason is phenomenological in the sense that for the vector leptoquark in the simplified model language, you really only need this one particle solution and you can address both anomalies at the same time. Okay. While in scalar models, you always need at least 2 new particles. So for instance, you can have a scalar singlet plus a scalar triplet leptoquark in order to resolve the anomaly, or there are also models where you have a singlet and a doublet and so on. But with a single particle solution, only the vector leptoquark works.
Oh, no, okay. So there is no other sort of no theoretical or what I was wondering whether with the other B data, there were some strong reasons to, from the structure of the current and so on, whether there were any reasons for scalar leptoquarks.
No, I wouldn't really say so that there is a more theoretical reason. Again, maybe one thing is that generically when you introduce new scalars in your theory, that you always have to worry about the hierarchy problem, but then obviously both the supersymmetric models and you can deal with it.
No, I mean that I am leaving out of the picture right now. But thanks for this very interesting exposition to the RD star. Thank you very much.
Yeah, thanks for the questions.
Yeah, thanks. Anyone else? Okay, Monika, I have a few questions. Okay. You said that BC to tau nu branching fraction could be now large. How large it could be from the experimental, I mean, from the measurement of lifetime?
I think well, it's a little bit different to pin to a precise number. So there have been some people claiming that it can be as large as 63%. So I would not really subscribe to the 3 simply because there are significant uncertainties, but I would say around 60% is certainly okay.
So, I mean, then with 60% number, I hope you will not have any problem with the scalar Leptokwa given. If you allow BC to tau nu tau to be 60%, is it? Because the major concern on scalar will come from this
some of the scalar Leptokwa models are actually more in trouble with these Monotower searches, but from the point of view of B sub CDK, I think that's not a problem really in that case. Yeah.
Yeah, exactly. Also, even if you consider in combination, like you have different type of scalar Leptokwa scenarios. So if you combine them, still it's a problem. I don't think so. It will be a problem.
Yeah. If you look at more than one Leptokwa, then of course the story also gets a little bit more involved. Yeah.
Also, for RD star, what standard model value you are using?
We were using the one provided by HFLAV.
HFLAV.
So that's basically the fit. Of
so it's like 2.252 or 253 or 257, the earlier one.
I don't remember the exact number.
Okay. Yeah, because things, I mean, like if you have, let's say, the value like around 0.261 or 262 or 263, how the conclusion will change? Do you have any idea of it?
Yeah, I mean, if you're depending on the standard model prediction, of course, the things change a little bit if you change the standard model prediction because of your form factors or other ingredients.
But
I think the impact of the standard model prediction is relatively minor because the much bigger uncertainty is in the experimental result anyway than in the standard model prediction.
Okay. Still, your conclusion will be valid, you were saying?
I'm pretty confident, yes.
Okay, thanks. So anyone else have any question? Okay, I don't see. So Monika, you can continue then.
Yeah, okay. So let me continue with the second part of my talk, flavored dark matter and its LHC signatures. And here I have to start by motivating the concept of flavored dark matter. So we have pretty good indications that there is some dark matter out there in the universe in addition to the visible standard model matter. However, we don't really know what it is. We don't know how this dark matter couples to standard model particles, and we don't know whether it's just a single particle or whether there's an entire new dark sector. And in analogy to the ordinary standard model matter, it is quite straightforward to consider that this dark matter also might carry some flavor. So what we're going to assume here now is the dark matter indeed carries flavor and comes in multiple copies or generations. And the question is then if this simple assumption of a flavor structure in the dark sector is actually enough to save the WIMP, the weakly interacting massive particle. To be more concrete, what we consider is here written in the right-hand side of the slide. So we want to have a new coupling of the dark sector to the quarks of the standard model. Here we introduce 3 generations of dark matter labeled by chi j. Those couple to the 3 quarks generations qi via a colored scalar mediator. And the coupling is then parametrized by a coupling matrix lambda, which is a 3x3 matrix due to the 3 standard model quark generation and the 3 dark generations taking place in this interaction. To be more specific, I want to address in this talk the case of top flavored dark matter. In the case of top flavored dark matter, the quarks that we are coupling to in this interaction are the right-handed uptype quarks with, again, a 3x3 coupling matrix between 3 flavors of fermionic dark matter. We choose it to be a Dirac fermion and the 3 standard model uptype quarks up, charm, and top. And what we want to assume, in addition to having such a coupling structure, is first of all, that this coupling matrix lambda is a new source of flavor violation. but it constitutes, in fact, the only new source of flavor violation. We call this concept dark minimal flavor violation in reference to the case of minimal flavor violation in the visible sector, where you have only the only flavor breaking by the standard model you cover coupling. Now here we extend the flavor breaking by having this one additional new source of flavor violation. Another assumption which is motivated from the phenomenology is the fact that dark matter, the lightest state out of the three dark flavor states, is top flavored. And that means this, that the lightest state, which is the stable one and constitutes the dark matter of the universe, actually couples dominantly to the third generation of the standard model, meaning to the top quark. Now, there are a few consequences of this assumption of having only one single new source of flavor violation. And the first one consequence is that the mass matrix in the dark sector is actually not arbitrary, but it has to have a certain structure, because otherwise it would constitute an additional source of flavor violation. So since the only new source of flavor violation is given by lambda, the mass matrix has to take this form. The leading term has to be just proportional to the unit matrix, and then you get corrections which are driven by the non-universality in this coupling matrix lambda. A second consequence of this dark minimal flavor violation assumption is actually a rather neat one, and that is the stability of dark matter. And the reason is that from the flavor symmetry assumption that we have taken, you obtain a residual unbroken C3 symmetry in the dark sector, which then guarantees the stability of the lightest particle in the dark sector, namely the dark matter. And thirdly, this assumption of having only one new source of flavor violation also helps us to reduce the parameters of the model, and we can conveniently parameterize this new coupling matrix in terms of the product of a unitary matrix U times a diagonal matrix D. And then the unitary matrix U has overall 6 parameters, 6 physical ones, which are 3 mixing angles and 3 complex phases. And the diagonal matrix in here, which are often also referred to as the coupling strengths in the model, those are real parameters on the diagonal of the matrix, and they have to be non-negative also without loss of generality. Now, once we have set up the model, the question is, how can we constrain such a model, or how could we in the future hopefully detect it? And in addition to the standard detection processes for dark matter in terms of direct dark matter detection in liquid xenon experiments, constraints from the relic abundance of dark matter in terms of the annihilation cross-section, and direct searches at the LHC for the new particles, in the case of a flavor violating interaction between the standard model and dark matter, we also get constraints from precision flavor data. And in the case of our top flavored dark matter model, the main constraints from the flavor sector come from D0, D0 bar mixing. The reason being that we are coupling to the up-type quark sector of the standard model. And from D0, D0 bar mixing, maybe not surprisingly, we obtain constraints on the coupling structure between the first and the second generation. Essentially, what we find is that this mixing angle between the first and the second generation in the coupling matrix lambda has to be small unless the first 2 generations are quasi-degenerate, which also relates to the couplings between these two, for these 2 generations being essentially the same. The second set of constraints stems from the observed relic abundance of the universe when we assume dark matter to be the relic of a thermal freeze-out. And here, what I would like to point out is that the fact that we assumed a non-trivial flavor structure in the dark sector actually leads to different freeze-out scenarios depending on the parameters in the dark sector. In particular, what is important here is the mass splitting between the different dark generations, because the heavier generations are in general unstable. They will decay to the lightest generation, but the lifetime heavily depends on the mass splitting between the different generations. So if you have a small mass splitting, then the lifetime of the heavier states will be relatively long, meaning that at the time the dark matter freeze out happens, all three flavors will still be present and contribute to the effective annihilation cross-section. While on the other hand, if you have a significant mass splitting, then the decay of the heavier flavors will be rapid. And at the time of freeze out, effectively, you can consider only the lightest dark flavor to be present and only that flavor contributing to the effective annihilation cross-section. Now, this means that quantitatively, the constraints on the coupling matrix will be somewhat different in the two scenarios, but qualitatively, the picture remains the same, that the annihilation cross-section relates the mediator mass, the dark matter mass, and the coupling parameters in the dark sector, these entries of the diagonal matrix D. Thirdly, we also get constraints from direct detection experiments, and currently these are mostly the xenon experiments, where you scatter dark matter of the xenon nuclei in a liquid xenon detector. And here, again, something peculiar happens for the case of flavored dark matter, in particular for the case of top flavored dark matter. And that is that in addition to the usual tree-level diagram for the scattering of dark matter of the quarks in the nucleon, you also get a contribution from a one-loop Z-penguin diagram, which becomes important if the quark running in the loop is a top quark, since this diagram is proportional to the quark mass squared. And as it turns out, these two contributions, tree-level and Z-penguin, come with a relative minus sign. So this minus sign means that you have a partial cancellation between these two contributions and thereby can actually partly avoid the stringent constraints that you get on the dark matter and scattering cross-section from the liquid xenon experiments. And for the experts in the audience, I would briefly like to mention that this model is actually a realization of the so-called xenophobic dark matter scenario. So xenophobic here doesn't mean that dark matter is racist, but it means that it avoids the coupling to xenon in particular. So you're not avoiding in general the coupling of this of dark matter to nucleons, but you are avoiding specifically the coupling to xenon, relying on this peculiar cancellation. Now, in order to have this cancellation work, you need a certain relative size of these two contributions, and the size of these contributions is driven by the parameters of the model. In particular, the tree-level diagram is heavily governed by the mixing angle between the first and third generation, since you have top flavored dark matter, meaning third generation, but first generation up quarks. So having this tree-level diagram of the right size means that you need to have a small, however non-zero mixing angle theta 1,3. And another lesson that we can learn from this pattern is that while with the current sensitivity of the liquid xenon experiment, this cancellation still works very well, with the future sensitivity of future experiments, which have even larger amounts of liquid xenon, the cancellation between these two contributions will actually no longer be sufficiently effective for all the xenon isotopes in the detector. And therefore, in that case, we will also obtain an upper bound on the coupling parameters D in particular. Now, from these different constraints, we can then place rather stringent limits on the parameter space of our model. And from these limits, we can then derive benchmark scenarios, which are still viable in terms of all these constraints, which we can then study in depth for potential LHC signatures. Now, when talking about LHC signatures, as I said, we need to define benchmark scenarios. And for the sake of simplicity, we just define two benchmark cases for the two different freeze-out scenarios, because those are really the qualitatively different scenarios in our model. Here you can see the benchmark case for the single flavor freeze-out scenario and the quasi-degenerate freeze-out scenario. The most notable difference is the difference in the choice of the coupling parameters. So you see that in the single flavor freeze-out scenario, the third generation coupling is quite a bit larger than the couplings of the first two generation. The reason is that the difference in these coupling parameters drives the mass splitting in the dark sector, which we need to have for single flavor freeze-out. The splitting, on the other hand, has to be much smaller in the quasi-degenerate freeze-out scenario. You also notice that the 1,3 mixing, as I've told you before, has to be small but non-zero. This is also reflected in our choice of benchmark scenarios. Now, what is left when defining these benchmark scenarios are two free parameters. One of them is the mass of the mediator, M5, and the other one is the size of the coupling parameter, d lambda 11. That's the first generation coupling. The other generation couplings are then defined through these relations. And last but not least, I would also like to mention that the CP phases that we also have in general in our coupling matrix are actually irrelevant for our study of LHC constraints, and we hence set them to 0 for simplicity. Now, concerning top flavored dark matter at the LHC, we first of all need to worry about LHC constraints, and they actually are quite strong already. And the reason is that our mediator particle, the scalar mediator which carries QCD color, is actually abundantly produced at the LHC through both QCD interactions and also the T-channel exchange of a dark matter particle, depending on the size of this coupling parameter of the dark sector to the first generation. And therefore, from this pair production of the mediator, we actually get the most stringent constraints from the LHC on the model. Now, the signature of mediator pair production are actually very similar to the case of squarks in supersymmetry, because like in SUSY, for the case of squarks, the mediator will decay into a quark in association with missing energy, namely with one of the dark sector particles. And then you get final states like TT bar plus missing transverse energy, or jets plus missing transverse energy, for which existing searches from the LHC can be recasted in order to obtain limits on our model. And needless to say, the relative rates for these different final states, whether you have tops or light jets in the final state, depends on the dark matter flavor structure, because the flavor structure determines the branching ratio of the mediator into the various final states. Now, here are the results of our recasting. Again, it's Run-2 data from the LHC, performed in a taken in a multi-jet plus missing energy analysis provided by CMS. And here you see in red the exclusion contours from TT bar plus MET, and in blue the contour from jets plus missing energy. And you see, as expected, that the sensitivity of these searches depends on the overall coupling strength. And this is largely due to the fact that in addition to the QCD contribution to mediator pair production, you also have this T-channel contribution from dark matter exchange, which is driven by the coupling strengths of the model. You see that in particular in this moderate coupling regime, the limits in the quasi-degenerate freeze-out scenario are quite a bit weaker. And the reason in this case is that the couplings in this case have to be approximately equal to each other due to the near degeneracy in the masses. And this means that if D1 is a moderate value, then also the third generation coupling, which is relevant for the TT bar final state, is still of moderate size. While in the single flavor freeze-out scenario, if the first generation coupling is around 0.6, then the third generation coupling is around 1.6. So that makes the branching ratio into the third generation quite a bit larger, so that the constraint becomes stronger. Lastly, what you also see is the prediction from the model in terms of the annihilation cross-section. So the thermal relic scenario, where the right annihilation cross-section is predicted in order to give you the right dark matter abundance in the universe, that's indicated by the orange dashed line. And you see that the scenario is still viable in the single flavor freeze-out scenario, but in the quasi-degenerate freeze-out scenario, this is excluded by the LHC searches for multi-jet plus missing energy final state. You can try to avoid this problem by trying to extend your model so that you do not need to comply with this thermal Rayleigh constraint anymore, but this certainly makes the scenario a little bit less appealing. Now, so far so good on the existing constraints. However, this is not all that the model can do for us. But instead, from the scenario of top flavored dark matter, we also obtain flavor violating final states at the LHC. And the first and rather obvious case is that if you again look at pair production of this colored mediator, in addition to these flavor conserving tops plus missing energy and jets plus missing energy final states, you can also have a flavor violating case where you have one single top quark, a jet, and missing transverse energy in the final state if only one of the mediators decays into top and the other one into upward charm. And second, you can also draw diagrams in which instead of pair producing the mediator, you only have contributions from a single mediator in your diagram. And in those cases, you can also get final states with only a single top, so-called monotop, in association with missing transverse energy. Now, the first channel, as far as I know, has not yet been searched for by the experimental collaborations. For the monotop signatures, there are searches. However, the kinematics of the final state assumed in those searches are different from what we have in our model. And therefore, we did not attempt to do a recasting of the existing search. Instead, what we try to do is we try to design new analysis which can specifically target our model both in the top plus jet final state and in the monotop final state. And here you can see what we found. So the solid curves in green and purple are the predictions of the reach with a 137 inverse femtobarn analysis based on 14 TeV data. And you see that already this amount of data gives you a further reach in the parameter space of the model than what is currently excluded by the LHC searches shown by the blue shaded region. You also see that the this thermal freeze-out scenario in the single flavor freeze-out case, which was still okay with the current bounds from CMS, could actually be probed by studying the single top, in particular the monotop signature. And last but not least, if you go from the currently available 137 inverse femtobarn to future sensitivities of the LHC, for instance, here the dashed contours show you 300 inverse femtobarn. And then further, if you go to 3 inverse attobarn at the high luminosity LHC, you see that these flavor violating searches actually do have a significant discovery reach in future runs of the LHC, and in particular at the high lumi phase of the LHC. So with that, I would like to come to the conclusion of the second part of my talk. And I would like to have shown you here that flavored dark matter can indeed reconcile the WIMP hypothesis with the data. And it's quite interesting to see that there is a strong interplay of the phenomenological constraints from flavor physics, direct dark matter detection, and dark matter relic abundance that shape the model and also have to be fed in when studying predictions for collider data. I've mainly focused on the case of top flavored dark matter here, where we have seen that a viable WIMP model can still be obtained in this case, despite the stringent constraints from the various types of experiments. And we have also seen that this model induces single top signatures at the LHC as very promising future search channels. So finally, to wrap up, I would like to come back to the slide that I've shown you in the beginning of my talk, where I've shown you the 3 different subfields of particle physics. And I would like to conclude by stressing that these different subfields are really strongly connected in particle physics, and you have to take into account the interplay between flavor physics, the high energy frontier, and cosmology in order to obtain the most information from the synergy of the different fields. So with that, I would like to finish and thank you for your attention.
Thanks, Monika, for this nice talk. So now we are open for questions. So please, okay. Rohini, do you want to ask questions? You have.
Yes, I want to ask a question on the second part.
Please go ahead.
Can I?
Please go ahead.
Okay, thank you.
Yeah, yes. Yeah.
So, very interesting, Monika. I wanted to ask one question briefly. Is that you mentioned somewhere that all the CP phases were 0. Now, supposing there are some non-trivial CP structure to your scalars, mediators, does your model have any issues? I'll tell you why I'm asking the question once I get the answer for this question. Because you made somewhere a statement that you put all the CP phases to be 0.
Yes, for the LHC analysis, yes.
Yeah. Now, the point I'm sort of making is that if there are some CP non-trivial phases, and because of that, if your scalar happens to be not a CP, I mean, I'm curious whether your scalar is a CP eigenstate. If it is not a CP eigenstate, at the top, you can have some very nice final state features on the top polarization in the LHC searches. So
this is a very interesting question, and I have actually not thought about this at all.
Because I had done this kind of a thing with one of the, it was just a master's thesis and we never published it, but we didn't have a specific model, and we had a mediator, which we said, perhaps let's assume that the mediator is not a CP eigenstate.
Yeah.
And then we found some very interesting reach through the polarization studies of the top in the single top channel, particularly.
Okay.
So I was just curious whether in your model this thing exists, because you have a very well-structured model. And of course, this will have implications for your first, to begin with, for the dark matter considerations also. But I'm just curious. I mean, that seems like a possibility of extending the model in one direction.
Yeah, it sounds very interesting, and I must say I haven't thought about this at all. So unfortunately, I cannot answer your question, but I will certainly think more about it. Thanks a lot.
So thanks, but thanks for a very, very clear talk and for very interesting work. Thank you very much.
Yeah. Thanks, Nandi. Jim, do you have a question?
Yes. So firstly, thank you, Monika. This was very, very interesting, and also, as Rohini said, very clear. This xenophobic dark matter, I'd not heard of this before, but you mentioned that with the larger detectors, LZ and Darwin, they'll be able to differentiate because of the different isotopes that are there. I didn't quite understand why that has an impact on this destructive interference.
Yeah, okay. I did not really have time to explain this idea further. So the idea is that you have a scattering of the proton of your dark matter and of the neutron. And these two amplitudes of scattering of proton and of neutron interfere destructively with each other. Now in xenon, you have a certain ratio of protons versus neutrons, and this is specific to xenon. That's why by just choosing the right coupling strengths to protons versus neutrons and having a relative minus sign in them, you can essentially avoid the scattering of xenon while not avoiding other nuclei. And then once you buy into that idea that you can basically fine-tune the couplings to protons and neutrons, you can go further and ask yourself, well, I have different isotopes of xenon in my detector, and for those, the ratio of protons versus neutrons is not exactly equal to each other because the different isotopes have different numbers of neutrons in them. So if you go to future sensitivity xenon detectors, at that point, the cancellation will no longer be sufficient simply because you cannot avoid the contributions from all the isotopes at the same time.
Okay, okay, yeah, I've understood. So thank you, Monika.
Okay, thanks, Jim. So anyone else? Okay. So I have one more general things. I mean, not probably just. So like you are talking here also about a simplified model, right? So and then you are getting some sort of conclusions. Now, point is that if you think about some UV complete model, okay. I mean, how do you think that conclusion might change? I mean, do any thought on this?
So I mean, basically, we can think about the different parts of the constraints that we have on the model. And well, the first sector where you might worry about different additional contributions from your UV complete model is, of course, flavor physics, because flavor physics is in general sensitive to high contributions from high scales.
Yeah.
However, we have taken this this assumption that the only new source of flavor violation is the coupling matrix lambda. And as long as you take this assumption, then even if you have some additional contributions to your flavor observables, then they will still be sensitive to the same combination of this coupling matrix lambda. And therefore, the constraints in that case will not change significantly, because you're still kind of measuring the same parameters of lambda, even if the prefactor in terms of new particle masses and so on is still is affected by your UV completion. So that's one thing. And then the other contributions are, well, for direct detection experiments, I would again expect the effect of an UV completion not so stringent, since the additional particles that you would introduce would be heavier than what you have in the simplified model. So you would get an additional suppression by their energy scale. Also for LHC, I mean, in pretty much any LHC studies, people consider simplified models for the simple fact that if the rest of the world is heavier, then those few particles that are considering, they are not that relevant for the LHC. And also for dark matter freeze out, what is mostly relevant is the lightest state that is still there when the freeze out happens. So overall, for the phenomenology, I'm not expecting a significant impact actually of a UV completion, but from the theory point of view, it would of course be very interesting to have a more UV complete model to motivate where this flavor structure is coming from.
Okay, because conclusion might change, right? That's why I'm a bit always curious how things will change.
Yeah, I mean, I would say conclusions may change in the sense that trying to construct a UV complete model might tell you something about what structure really is allowed or is not allowed within this model. Because, I mean, if you think about that dark matter should have a flavor structure like the standard model does, then you would also maybe would be tempted to think about some grand unification where dark matter and standard model matter really have a common origin, because otherwise, why should there be 3 generations in both sectors? And then this assumption of having some grand unified picture of both standard model matter and dark matter, this will probably then give you also some constraints on what the coupling structure between the 2 sectors might look like, and so on and so forth. But yeah, this is definitely left for future work.
Okay. Yeah, thanks, Monika. So any further question? Okay. I don't see anyone raising his or her hand. So let us thanks again, Monika. So I'm handing over now to Jim. Jim, you want to say something to Monika? Yeah, clapping, definitely. We should clap.
It's hard online. Yeah, thank you very much, Monika, and thank you, Soumitra, for handling the session.
So, yeah, thanks again for inviting me for this talk. It was really fun.